Okay, so in this problem, we have a cylinder that's mounted on this rod, right? So it can rotate around this rod. And we're taking this little wad of clay and we're shooting it at the cylinder, okay? Um, so we want to know, what is the question here? I think we're trying to find the, hopefully it's rotating afterwards, right? So it's initially at rest. Uh, the line of motion of the projectile is perpendicular to the axis at a distance d is less than r from the center, okay? And we want to find the angular speed of the system just after the clay strikes. So we're looking for angular speed of the system. Okay. The moment of inertia around the cylinder, we're given that, right? Just for a cylinder. Um, and the moment of inertia of a point mass particle is this guy. So this is just the how much this I would be for just a point mass. So the clay blob is like a little point mass being stuck to the system. Okay, so two things. So this is an inelastic collision because the wad of clay is sticking to the cylinder. And what we know from inelastic collisions is that we're not using conservation of energy here. So conservation momentum is fine. The cylinder rotates after the collision, which can make things a little bit difficult. So we, yeah, we're looking at different points essentially. So we're going to start with finding the final angular momentum, and then we're going to relate it to the initial. So this problem won't be super complicated, but there's something I really want to point out that I think is very important for a point mass. If I have, okay, maybe I'll model it as an object. If I'm going to figure out the rotational or the angular momentum that's caused by a point mass, so any type of point mass moving with some sort of velocity, I can choose an arbitrary point that's a radius kind of at any point and call this r. And I can say how much angular momentum would this cause if it was rotating around a radius. And this works very well for problems where it's going to collide into an object and that linear momentum is going to become angular momentum. So the way that we model that is we're going to use this equation, right? So we're just going to look at the initial first, I guess here. So initial, we know that we have some IW, right? And we're going to sub a couple of things. So when we have a point mass, which we do when we have this little wad of clay, when we have a point mass, we have the sort of mr squared, right, for that point mass. Let me just use the same convention. Well, in this case, it's actually a d distance, d. So this would be the distance that it would be away. And we'll call this d. We'll stick with what's actually going on in the problem. Okay, and d squared, right? But then also, this v is essentially like a perpendicular velocity. If we want to model, so we know that w, right, is equal to this tangential velocity, v tangent, over the radius, right, that it's acting away from, right? So normally we see it as over r. So like the general expression would be w is equal to vt over r. We can actually sub that into this expression, right? And so I think that we'll say vi is our v tangent here, vi, and then our radius away from the center is still this d value, right? So that simplifies things for us nicely, right? Where we have this Li is equal to mdvi, right? So what we're saying with this is a particle that's moving with some sort of tangent velocity, okay? We're saying that like at this point, the rotational, the angular momentum that it would have is dependent on these things, right? So that's the angular momentum it's going to impart into the system. So this is our initial. Okay. What about final? What's happening finally in this system? So this is true basically for any particle, and you can model it like any distance away from a point. As it gets closer, like right when it strikes, this is what the radius would be here. But I'll show you an example kind of like where we're looking at the radius like further and further away, and there's kind of a little bit of a difference there. Okay. But I think for the problems for this class, it might be out of scope, but I'm not quite sure. Okay, so Final angular momentum. What is happening here? Okay, so what is rotating at the end? Well, we have two things that are stuck together, and they both have their own mass moment of inertia. So we have the mass moment of inertia of the this wheel thing, and then we have the mass moment of inertia of this clay, and then they have a shared angular velocity, right? Okay, so let's plug in what we have for those. So final, let's first look at these. So we have this guy would be, this is the wheel, right? And this is the clay. So let's just plug them in. So we have 1/2 mr squared for the wheel. And then for the clay, we have 1/2, let's see, clay. Yeah, we also have the same, so really important actually for this problem. Dun, dun. Okay, once it's impacting, right? So this is where we start, right? This is the initial energy that we, or the initial angular momentum that we start with. But after it makes contact, right? It's going to be making contact at the full radius, this full radial point, right? For the circle. Okay, so we have the initial that's going to take into account like the height it was when we started, where it made impact. And then for this guy here, we are actually, oh, sorry, I forgot the M. So that big M is the M of the disk, and then we need the little m of the wad of clay. I think I wrote that wrong there. Yep, sorry. For the wad of clay, this is a point mass. We don't have 1/2 for a point mass. We have little m. So M clay, and this is the big M is the M of the disk, okay? For the wheel. I keep calling it different things, sorry. It's also a cylinder, I don't think, and not a wheel. Okay. All right, LF. So to summarize. Okay, so we have our final, right? And inelastic, so our final is due to the shared mass moment of inertia of these two multiplied by W. The initial is due to this little point, right? Some distance away from whatever that center origin, some displacement away. And then we converted this, right? Because we use this IW expression, but we found that W is equal to this tangent velocity over the radius, just this general expression for angular velocity, okay, that we can sub in. So now that we have our pieces, we have Li is equal to Lf here. So mdvi is equal to 1/2 mr squared plus little m r squared, and then they both have this w term together. So let's see here. So we are trying to solve for w because we want this wf. That's what the problem asks us to find. So this is our final velocity, right? Because our final angular momentum should have our final angular velocity. Okay. So wf is equal to mdvi, right, divided by, and if I just pull out the r's, because I think they both have like an r squared term, so I'll just leave it like this. I don't think it really matters. 1/2 mr squared plus mr squared, right? And that's our final answer. Okay, so what did we learn here? What was the important takeaway? Okay, so in our final system, the point that it was rotating about the center of mass is going to be this r value, right? Because that's going to be where it's going to be rotating around. And then we took our initial angular momentum, and we went from basically Li to Lf. We did some algebra, and we solved for our Wf here, okay? This is kind of the tricky part for the system where we have that point mass radius, okay? So be aware of that. And then this was also a little bit of a tricky substitution here, where we use the fact that we know that this tangent velocity, right, we can set this equal to some angular velocity value and sub that into our problem. So I will post the solutions for this one too. There's a little bit of a nice written description in there as well. All right, moving on to the next problem.